So I'm back again, and now we're talking about advanced shape and texture. And again, a lot of books, and yeah, about the same list of. So the John Ross is coming back again. One interesting thing is this paper, which I'm going to talk about later. And then we have the curvature part also here. So the first thing we are going to look at is our distance maps and their relative thickness map, and then looking at different characteristic shapes. And to round off, I'm also going to look at texture analysis. So the first question is how we can measure the size of complex objects. Interesting thing is also here to look at sizes that are relevant for the study of the object. So for example, in porous media, what are the sizes relevant for diffusion and local processes? And also we want to see how objects grow, and are there some characteristic shape metrics that we can look at? The other thing is looking at patterns, and then we come into the texture analysis. And then we look at different patterns in images and see if we can compare them and put numbers of them. Well, you can also use words like radiologists say, this thing is looking evil, but what does it really mean? So from that, it's probably that this blob has some kind of pattern in it that looks not very nice. So the first thing now is to look at distance maps and what they are. And first of all, we go back to creating some image. And in this case, it's just a plain blob. And the distance map is a map that, or image actually, that shows the distance from either the background or the foreground into the other side. So if we have the background and looking into the foreground objects, we can measure the distance for each pixel in this object, how far away it is from the closest parameter point. And we have different metrics to do this. Euclideans with some approximations. We have city block, which is 4 connected, and checkerboard, which is 8 connected. And they give a little bit different distance maps, how they behave. So first of all, we have a very nice function that does it for us. So there is this in ND image distance transform EDT. So it's Euclidean distance transform. And with that, you compute, you have some parameters here to play with, but the main thing that we are using is this function. So it's very simple to use. You only add the black and white image, and then you get distance map. And from the image we had before, you can see that all the parameter pixels, they have distance 1. The ones at diagonal contact has 1.4. If you have a straight line, a 2 here, and then this one is, this is square root of 5 or something. And this is probably square root of, let's see, 9 plus 4, 13. Yeah, no, not 13. Yeah, anyway, so you can see that the distances, they increase the further away you get from the parameter. And this can be done on different ways. We have different algorithms. In some cases, we have the exact distance transform, which gives us this. There is some brute force algorithm. I don't know how it's done. It's probably pretty detailed. So it's for each pixel, it's searching for the closest background. So that's not very efficient. And then there is an approximation called chamfer distance. There are also many variations of that one, but this one is giving you only full integer steps of the distance. You can see that there is a difference between the distance values in this one and in the other two. For example, you don't get the diagonals, and also the values in this one are shorter. So, well, actually, let's go back again. What you can see here is also the execution time. The exact transform did it in 25 microseconds. The brute force did it in 60 microseconds, while the chamfer distance did it in 22. Microseconds is not a big deal. You can do it easily, but now consider this is a 9x9 image. And when you come to real data, a typical image from a tomography experiment is something like 2000 times 2000, 2,500 squared. So it's a really huge volume. And then we start getting into time travel. In particular, if you want to produce a series of those and do comparisons of distances, then it's really important to have a fast algorithm to compute the distance. So just as an example, to put it in, extrapolate into what it takes to compute on larger images. So this is now a 512 by 512 image. The exact transform took now 19 milliseconds. The brute force took more than 700 milliseconds. And the chamfer distance did it in 3 milliseconds. So there's a huge difference between those. And if we extrapolate that into volume scan, we are talking about 28 minutes, 11 hours almost, and 4 minutes. And that's a huge difference in how long you have to wait, in particular if you have many data to process. The cost, however, to get it this fast is you can already see that the distance field has a strange shape. It's not as homogeneous as you would want it to have it from the exact transform. However, depending on what you want to do, this may be sufficient. For example, if you want to have it as a elevation map for watershed segmentation, possibly this is enough to get your objects, and then you're fine with it, and then you can work with a fast version. In other cases, if you want to do quantification based on the distances, you need the exact transform. So let's look at different how to compute it. Here is a little simple distance iteration. Again, we're not saying this is the most efficient way, but at least it demonstrates how it's done. And the important thing is here is the way what you have, how you compute the distance for a specific point. So let's execute that one and go out, and let's run it on our little dot. And now we run this distance transform. You can see how it propagates through the image. The initialization is a very large distance. You can see here 255. And that minimizes pretty quick. It's kind of more like a marker telling that this is not yet processed. But you can see here that in 5 iterations, this object has been measured. We have different distance maps. So let's look at what when we have the Manhattan or city block distance. Then it's not the Euclidean distance anymore, but it's the absolute distance between x and y, x minus y vector. And then we implement like this. You remember maybe before we had the square root, but now it's the absolute distance in X and Y direction. And that gives us our distance. And that looks a little bit different when we run it. So here we have the iterations again. You can see that it's more looking like the chamfer distance that we had before. So it's taking only integer values in this case. And it's a difference in what you see. And the advantage of this one is that it's much faster to compute than the Euclidean distance, which requires that you square and take the square root for each pixel computation, while this one is only taking the absolute value between the distance to the nearest edges. Another thing is also about where you have to be careful. Normally, we talk about isotropic voxels, so then it's fine. So, for example, have a voxel size of 1 micron in each direction, that's fine. But what happens when we have anisotropic voxels? We could do a resampling to get into isotropic scale. That would be a possibility. Or the other one would be to have a custom distance map that actually takes the different sizes, the different directions into account in, instead of assuming 1 by 1 by 1 size. And also distance maps, they can't be better than you resolve things. So if you have a small object, it may not be so precise. The larger the object, the more precise you get your distance within the object. So what does it show? We have two cases. I briefly mentioned it before. So you can do distance from the foreground into the background. So that gives information about how far in you are within the object, and also, of course, the object size. And the other one is that you take from the background to the foreground, and that would be more about measuring this distance or space between objects. Let's look at this, what it looks like. We have two cases. We have the bi-level image, and within the object, we can measure how far away one voxel is from the background. You can also more or less say how thick it is. If you look background to foreground instead, you see that now we're measuring away from the object, and then you can see that how far away a pixel is from the object itself. So let's look at some different cases here again. Oh, this is a big one. I think I need to actually go over in the other way. Otherwise, we don't see anything. Let's see. Something was supposed to happen here. That was not good, but let's run this one instead. Let's run an animation of frames and see what happens. So now we can see a little bit more. So now we have an example where we have two objects and measure the distance between the objects. And no, sorry. We let an object grow and see how the distance changes. And at the same time, we do component labeling as a comparison, what happens when the objects are growing. And with the distance map, you can clearly see that there is about the same average distance within the object. But with component labeling, after a while, the objects grow together and you can't identify anymore that there are two objects. So they merge into a single object. And you can see it's also in the average area that at some point, the area is growing to a very large value. And that's the point when they merge together, and then all of a sudden you calculate the whole object area. So these were just examples of constructed blobs. So let's see what it looks like in real images. So for this, we take the bone filters, the bone slices, and we have here the mask, the segmented mask of the different pores. And then we can take a foreground map. So we look at how big are the objects within, how big are these objects. The other way would be to look at the background map, and that looks quite psychedelic, first of all. But anyway, you can see how far away these objects are. In particular, if we would follow the ridges between these objects, and you could tell how far is the how close or how far away different objects are from each other. Let's look at the cortex image. Now we look at only at the mask that was provided, and then we can also see that there is a very distinct line here, which tells that it's a small, it's a narrow object, and if we follow this, we could actually get the thickness out of the object multiplied by 2, and then we get it. But it doesn't really tell the information we want to know. So distances are good in one way, but it's not always the information we need to look at. So let's look at the histogram out of this cortex image. You can see that the histogram is more or less a smooth function. It doesn't give any bumps. It doesn't tell really much. It only tells that we have on different ISO levels, we have so and so many pixels, which makes sense because it's like you're peeling off an object layer by layer. And in the end, you can see that there are very few with the values 50, and those are the ones out here on its edge. So that gave the idea to change into a different metric, which is the thickness map. It's related, but what it does is more about taking each point and drawing a sphere or circle with the radius that the distance tells you. And then you take the maximum value of those spheres. And if you compare the distance map to the pore size map or thickness map, you can see that the distance map gives very nice separation lines, whereas the pore size map tells more about how big is the largest pore between these objects. And that's very useful, for example, in porous media experiments. You can even relate the water retention to this pore size map. And that's a very useful concept to compute. It also tells you how big are the pores. For example, how big is the separation in this area in a much better way than the distance map, where you have to locate this ridge. Let's look at one image. Instead, we had before, we had distance maps as you saw them before. And now as a comparison, we look at the thickness map. I need to run that one. And I need to go on the next slide. And looking at them, now all of a sudden, instead of getting the ISO line wise, now we can see that this area belongs to a pore that has a certain distance. That's mostly more useful than just the distance itself. And that one I need to run. So look at the different thicknesses. I need to change here. Then you can see that in this image, we have, so in the foreground, we have the objects. And you can already see by eye that we have 3 different categories of objects, very small ones, intermediate size, and the large ones. And that one comes out very nicely in the thickness map. We have a collection of small objects, we have some larger objects, and then we have really large objects. So that already gives us a better separation between the objects than the distance map did. Of course, you can do area calculation, of course, but this is a different way of looking at it. And looking at the background, you can also see that in this object, we have kind of a general distance between objects is around 25-30 voxels. And then there is a very large one around here, which is probably represented by those gray blobs here. So that's a very remote objects in these areas. Of course, you can go into 3D, and that is also possible. And let's load a 3D image. So we have this bubble data, and we have some slices through it. And so it's actually inverse porous medium, because each bubble in this foam is like the grains in the porous media. And now we need to do a calculation. It takes a little time to do it. And let's see how it works. Looks like it got stuck right now. There it comes. So now we get a very nice mesh of the data. You can see how the bubbles are connected with each other. Here we actually use the Martian cubes algorithm to get this match, and it shows how it can be used. And now looking at a little bit of a close-up on these plateaus, and you can see that there is a lot of pores, and you can rotate it in different ways if you like. Getting these things to work, you may need to install some extra packages. And please tell me if you need help in finding those packages that you need, because they are not always obvious how to install them. So let's look at the bubble distance transform. We have computed it for the different slices in the image. And now, as a comparison, we can look at what it looks like with the thickness map instead. So here you have an image of the foam, and you can see that this is a very large bubble, smaller bubbles, and they're nicely colored already through the thickness map. And in particular, as bubbles are mostly very spherical, there are not very large variations between them. So let's look at the bubbles and see how the map looks like for that. This also takes a little while to compute. And this depends very much on the computer you have at hand to compute it. But in the end, we will have a thickness map of this bubble image. So it's at 50%, so it's not really, it takes a little while to get here. So let's see, can we do something in between? Well, yeah, it's almost done now. So let's see what comes up. No, yeah, there we got it. And let's go on the next one and look at this. And then you can see here what the bubbles are looking like. And you can see that there are more or less connected areas. In some cases, we have fatter bubbles, and they're kind of overlain in each other. So in this case, we have overlay projection of in each direction. And then we can also look at the different slices and see where the bubbles are and how big they are. Each gets its color from the size. And of course, in 3D, it's always interesting to see it in volume rendered. And for that, I use now IPyVolume. I think we used it before in one of the lectures. You need a couple of extra grips to get that working, installing some Python extension or Jupyter extension to get it running. But I have the recipe to do it if you need help. So this is what it looks like when we look at these bubbles. Some are larger, some are smaller. You also have some interactions, so you can do opacity with this one. So it's a nice tool. It's a bit coarse rendering right now, but it's more about computation time and rendering time to get that. Let's see. Yep. Let's go on to that one. We always have, in many experiments, we are talking about, we want to know surface, how big, what happens around the surface or an interface between different things. And so therefore, it's very important to identify these volumes or areas. Usually, interfaces and surfaces are one dimension lower. So the surface area is would be in 3D and the perimeter is in 2D. So the perimeter is just a line around the object. So it's kind of a 1.5D. And the surface area is 2.5D because it's just a surface that we're talking about. And then it can be used for getting the connectivity of networks, of cells, for example, or also in the porous media, the network of pores to get the connectivity. So you have here a couple of different applications where you can need this information. And also, if you do erosion and dilation, you have to be very careful because by dilation, you may close some pores, and by erosion, you may open up some new pores. So you have to be really careful about that. And that also changes the surface area. And so be careful when you apply these methods. Even though I show that as a way to clean up images, you have to do it with care. Let's come back to the meshing again. We want to do these finite element modeling, and let's see what we can do with it. So one thing we can compute is actually the curvature, see how much the surface is bending. A low curvature means a very large radius, so almost flat area, while a small curvature, a high curvature means that it's a very pointy place. Let's look at this, where you can use it. You can, for example, compute the surface normal, which is useful in some physical simulations. You need to know how things bounces off this area. Also for, I think for fluid simulations, you have some need of knowing this. Very useful. It's for ray tracing. So when you do nice renderings, you really need to know where the normal is because the light reflects around the normal. And if you want to have a nice reflection result, then you need to know where you have the normal. Curvatures in 3D, you have curvatures in two directions. The widest and the most narrow point of that position. And the curvature is actually one part of the calculations in inverse scale space filter with total variation. It's actually the curvature is used in that one to calculate how the filtering is working. Also in some diffusion filters, you need to compute the curvature of the data, of the image locally. But then it's an analytical curvature that we're talking about. And now we're talking about surfaces. So it has two principal curvatures, and it's difficult sometimes to measure, to display this, so or measure this. So it's often that people are using the mean curvature, which is just taking the average value, or the Gaussian curvature, which is the product between the two. Then we can see what it looks like. We have here an image of the mean curvature and the Gauss curvature. You don't see much difference between these, maybe because of the structures that are in this example. But anyway, it's a different way to look at how the image is curving, or all the information is curving within the image. You can also use it to calculate the characteristic shape of the object. You can find saddle points within how much saddle points you have in the image, etc. So it's a metric that you can use on images, and in particular, you have visual indications on structural changes in the objects. So if you have something that you're compressing and looking at, these are metrics that you can use for characterizing that. So we have some other techniques. Well, finding different techniques for quantifying structures. In some cases, you can take some general recipes. You can test something in, for example, in Fiji. Other volume rendering tools like Volvis. Yes, Volvis, I think. It's 3D rendering tools. They provide you with a lot of metrics. Some of them, they are useful, the general ones, but in many cases, you have to look for metrics that apply to your specific application. So you have to come up with something yourself. In particular, if you need to do some model-based work, then you really need to look more into what is relevant for that particular model. Here's a little bit more references to look at if you want some reading. And let's jump to the last part of today's lecture, which is texture analysis. And it's about analyzing patterns in images. And well, we have a beautiful world with a lot of patterns in it. Here are some nice examples from a lecture in New Zealand. And you can see we have leaves, you have, I think that's some kind of rock or something, I don't know. But tree, it's tree, and fireworks, landscapes, etc., etc. Some cracky soil, stones, water. So different natural structures, they provide repetitive patterns, and they are called textures. They don't need to be perfectly periodic. They can have some stochastic behavior in them. And there is a lot of metrics how to characterize these textures. And often they are based on some kind of convolution of the neighborhoods, looking at local covariance. And let's look at some sample texture now. And we create a bunch of those. Here we have some. So this is just line patterns, some more or less connected blobs. And there should be a couple of more, which are not visible. A little bit more distorted things, a diagonal pattern. So these are some more generated textures. And what we now want is to analyze what we have. And one is looking at the co-occurrence matrix, which has different parameters. One is the distance from a pixel to another, and the other one is the difference in intensity, or the change in intensity. So, for example, here we look at pixel at position X and Y. Does it have value I? How about if then the pixel which is delta X and Y away has the value J, then we should give it a 1. And that's summed up in this co-occurrence matrix. And that can give us some kind of idea what the text will look like. And let's go on to the next slide. So what it looks like, also again, we have the co-location matrix is actually also provided in scikit-image under texture. And let's run that one. We get some different values here. And these can give us also nicer plots. So here we have our 6 patterns. And this is what the co-occurrence matrix looked like for these patterns. Some can continue, other ones not. And then we have the average co-occurrence, and they actually look a little bit more like each other. But they are very similar in the shape, though they are a little bit varying. So this one has higher frequencies than this one, for example. This one is more complex, so it has also more complex structures. And this one, again, looks more like the other two here. So that from that, we could more or less conclude that this is more, these two and this one, they have more or less the same texture, but it's a little bit different orientation. This one is kind of looking like this, but still not. And it's also seen here in the matrix. And so that can be used then to look at textures. The another one is looking at correlation between the mean difference between different locations. And this is what we have here. Let's see. And that should be shown in a different way. So here we have some kind of distance co-occurrence, that at some distance you see something that's well correlated, and at a different distance it's kind of anti-correlated. So it's in what we can see here now is the position of the bars and of the gray and the black bars, and that is what you can see here. This must be in the difference in the same direction, so it's just a flat line. There is no difference actually in the horizontal lines. In the pattern, you have a different co-occurrence, but it's more like the one of the bar pattern. This one is more confusing, so it's getting different values. Those two look more or less the same, so they get distance co-occurrence that's essentially the same value. The bar pattern, the diagonal pattern is also a bit confused now, so it's not as clear comparable to as the co-occurrence matrix. And then you can look also in different directions, and then you can see that this one and that one, they look the same, but there is a phase shift. That one is somewhat the same, but these have these are also categorized as more or less the same. So depending on variations in natural cases, you don't have so clear information, and it's also harder to make a clear distinction between which texture you have. But in some cases, you have very clear, distinct cases, and then it's fine. So now, as an example, let's take the brain image again with the cortex. And now it's a larger image, so we need to do something to compare different regions in it. So it's not only about taking the whole image and look at it, because then you have nothing to compare with and to look at. So what we do is we start dividing the image into smaller tiles. In this case, we are looking into 48 pixel wide tiles and see what comes out of that. We have now 10 tiles in that direction and 8 tiles in that direction. And now let's look at the texture properties in these tiles. And they need to be shown. So here we have different images, different tiles, and this one is essentially just the average gray level within the regions. Then we have some contrast, and all these metrics, they are described what they actually mean, are described on the scikit image feature help page. But anyway, it's about looking at how images are, different regions are correlated with within each other, and that gives you different patterns, and those patterns in turn can be then used within a machine learning algorithm, where you take these as features within the learning algorithm. So it's not usually you can't with a simple of these metrics, you can't just tell this is that and this is that, but it's more about a combination of different of these features that you combine to get the conclusion. And then you can see here that you have same number of pixels within each. You have some average value within them, and you can make some statistics around and see what happens in the different areas of these features. And what we can also look at is some scoring, looking at what they look together. I got a little bit of a warning here first, but there should be a plot showing the histograms and bivariate histograms. And soon it comes, I hope. So there we got it. So now we have the different metrics. We have the intensity mean. We have, oh, it's very tiny here, so it's hard to say. But anyway, the different metrics, and you can see that some, they're separating much between background and foreground, and others don't. And now we need to find combination that are helpful. You see down here, you have more or less a linear connection between two features. So this is the energy versus the homogeneity. And other ones, they are splitting out pretty much. So this one is separating nicely. So maybe this is a combination that we want to explore further to be able to separate different things in the image. But once we have identified some that produce interesting separations, we also need to look at what happens when we combine these into the image, doing segmentation about it. One thing about, more thing about the texture analysis is that you actually need to create tiles, so you get a coarser separation within the image. You can, of course, play with smaller regions, but at some point you go below the critical size to describe a texture, and then you can't with clearly tell if this is texture A or texture B. So you need some area or volume to describe the texture, but it shouldn't be too large, because then you would lose spatial feature in the image. So this is probably the smallest, or you could probably make it a little bit smaller, but not much larger, because then you would have really big blobs that would identify the cortex around here. So it's a balance, and when you do texture analysis, you have to really play with these values to get the most information out, most reliable information out of the image. So that brings us to the end of today's lecture, talking about different ways of characterizing items, first finding them, then afterwards we started doing measurements, looking at area, distances between objects, looking at orientations, positions, and now in the last part we also looked at textures. And actually everything can always be combined in a big recipe. So for example, if you make identify some cells in an image, some cells may have some characteristic texture, and then you can, with the help of the texture analysis within each object, you could also start doing analysis based on texture within cells to make classifications. Now, as not knowing much about cells and how they behave, this is just an assumption what you could do, or suggestion what you could do. If it really makes sense, I don't know, actually, to be honest. But that would be an idea how you could proceed on looking at combinations of these methods. So, well, with that, I say thank you for today, and see you in next week. And exercises, they should work. I checked them through for today. Data is available, and I got the question. You're welcome. So thank you. Well, let's see you next week. Bye-bye.